Okay. Oh no. As soon as I press record, it's turned. Okay. I hope this looks good. Yeah, I hope everything is good. Anyway, I will continue since that red thing has disappeared. I'll continue. Let me share my screen. And so I want to go right into chapter 12. I wanted to do this earlier today, but I had meetings that came up early in the morning, and then I had some meetings later on, and I was trying to get caught up with grading. So anyway, chapter 12 deals with compounds that have oxygen and sulfur, like it says right here. So we have seen some of these compounds before, but now we are focusing on them. So we saw them before in the context of all the different functional groups, but now we're saying we're taking time to study these and only these in this chapter. So we're going to be looking at three families of compounds that contain carbon atom singly bonded to oxygen or sulfur. So we're told here we're looking at a carbon atom that's directly bonded to an oxygen atom via a single bond, which remember, this is different from the carbon doubly bonded to oxygen. That one had a special name called carbonyl. Okay, this is a compound, the alcohol, the ether, and the thiol, we'll see the thiol, has a carbon attached to an oxygen, but it has to be via a single bond. Okay, so first group we're looking at is the alcohols. And with the alcohols, the example they gave us here is the ethanol. So if you draw the lowest structure, you can see the bond a lot clearer. You have a carbon on the end, carbon in the middle, and then attached to an oxygen here. So the bond they're talking about, that's the alcohol bond, is this bond right here. The bond between the carbon, oxygen, and the hydrogen. That direct bond is the alcohol bond. Okay? And of course, you have the rest of the molecule here. I'm going to fill in my hydrogens right there. I'm filling in my lone pairs here. So the highlighted portion of this is what's making the alcohol part. Now, we mostly tend to recognize the hydroxyl group, OH, attached to the carbon. But you have to have these three together to have an alcohol. What about the ether? With the ether, to have an ether, so with alcohol, we have COH, like Ca. With ether, you need COC combination. So in this case here, you have to have a carbon directly attached to an oxygen via a single bond, and then the oxygen is again attached to a carbon via a single bond. So we're dealing with this three, like right here. Now, the rest of the molecule can have more than two carbons, but you have to have a C attached to an O attached to a C. Now, the rest of the molecule, it can have a bunch of carbons. We really don't care, but as long as you have this combination here, COC, and then, of course, you have the hydrogens here, then you know, with that combination of letters, you have ether, or should I say elements, right? Okay, and then we're moving on with thiol. Thiol is just like an alcohol, but thi is another term for sulfur. Usually thiol refers to sulfur. And sulfur and oxygen are in the same group in the periodic table, so they have similar properties, okay? So in the periodic table, oxygen is right above sulfur, so these are in the same family. So instead of having an alcohol where this is oxygen, you just replace the oxygen with a sulfur, and this is called a thiol. So this is called ethane thiol. Don't worry, we won't spend a lot of time naming these because these are not very common. We will name alcohols, but we'll kind of extrapolate that naming to the thiol, even though it's not an exact extrapolation. We're not going to spend a lot of time naming thiols, but we will recognize them. So this is called an ethane thiol, okay? Moving on. Wow, we're right there. Label the hydroxyl groups, thiols, and ether oxygens. Okay, so we're going to go through here. I did modify the slides a little bit so it can be more targeted towards what our goals are. So we want to label each hydroxyl group, each thiol group. So the hydroxyl group, we want to find a carbon attached to an oxygen, right? And hydrogen. So it could be more like this. A carbon attached to an OH, right? Thiol, we know it's going to be a carbon attached to an SH. And then ether, a carbon attached to an OC. right? Like that, right? So COH, CSH, COC. That's what we're looking for, that combination. Okay, so let's see. We can start off by trying to find the easiest one, right? Why don't we start with the sulfur? So I'm going to try to find the thiol first. I'm looking for S, right? So let me go through here. Let me zoom this in. I don't see any S here. Ooh, there is a S, right? Do I see that combination I'm looking for? A C attached to an S attached to an H. Yes, right here. You all see that? So this will be my thiol right there. Okay. Let me see. Do I see another S somewhere here? An S. I usually find the element that stands out the most, and then I just kind of fill in the rest of it. Okay, so I found my thiol. I guess I could find my hydroxyl, right? With my hydroxyl, I'm looking for an oxygen first. Once I find it, I'm asking myself, is it attached to an H on one side and a C on the other side, right? If it's attached to an H on one side, C on the other side, it's a hydroxyl group. But if I find the oxygen and it's stuck between two carbons, it's an ether, right? So let's go looking for our oxygens. I see an oxygen here. And remember, in the skeletal structure, each corner atom is a carbon. So this is a carbon. So I see a COC here that makes this group an ether. And hopefully, as we're going over this over and over again, it's getting easier for you to pick out your functional groups, right? Okay, let's go over here. I'm looking for my oxygens. Okay, I see some oxygens, oxygen here, oxygen here, oxygen here. And this is a little hard to tell. Sorry for the fuzziness. And oxygen here. Okay, so let's start with the oxygen, this one here. Okay, I have an oxygen, but on one side I have a hydrogen, and on the other side I have a carbon. So we know that if we have HOC or COH, this is going to be alcohol. Okay, so this is going to be alcohol right here. Same thing over here, HOC, also alcohol. And then this one here is also alcohol because we have a O on one side, we have a H, on the other side we have a C. Okay, what about this one here? Let me go ahead and draw. I won't really draw it out, but I'll just kind of show you guys. This is a CH2. I think this is 5. Okay, so CH2 and this is 5. And this is attached to an O. Then we got CH2 and then 4. Bottom line is, if we were to draw this out, which would be hard to draw it out, but I think I can manage. Let me see. There is 5. 1, 2, 3, 4, 5. And then eventually attached to an O. And then 1, 2, 3, 4. That's what this is communicating. Bottom line, the oxygen is stuck between two carbons, making this an ether. Okay. Yes, this is salmeterol and is used for if you have asthma. They usually use all these drugs that end with all. Most of them, albuterol, salmeterol, something ends with all. You know, whenever a drug ends with all, most likely it has an alcohol in it. Okay. Okay, so now we're looking at two families of compounds that contain the carbonyl, right? We were looking at the oxygen and the sulfur, right? Now we're moving on from the carbon oxygen single bond. We're moving to the carbon oxygen double bond, the carbonyl. With the carbonyl, we're studying the aldehydes, which we've seen before, and the ketones together. Well, when you're trying to identify the functional group, how do you tell one from the other? With the aldehyde, the carbonyl, this is the group right here. This group is called carbonyl. So in the aldehyde, the carbonyl carbon is on the edge. In other words, it's like carbon number 1, right? So you number this one here, carbon number 1. It's in the far right. That's the first carbon you run into. So with the carbonyl carbon in the aldehyde, on one side, you will have a hydrogen. On the other side, you will have a carbon. So what we're looking for is this combo of elements. You have the carbonyl attached, the carbonyl is essentially a carbon attached to an oxygen through two bonds. Then on one side, you have to have a hydrogen. It can be to the right or to the left. So this combination of atoms here is mandatory. On the left side, it has to be a carbon. Okay, so technically, this whole thing here is a carbonyl. I mean, sorry, this whole thing here is an aldehyde. Well, actually, I take it back a little bit because, you know, with formaldehyde, you don't have a carbon here. So the element we're looking for all the time is this part here. So the rest of this here can be, it can be a hydrogen or a carbon or things like that. But essentially, this is what we're dealing with. When we see this combination, carbonyl, on one side it has a hydrogen, we know it's an aldehyde. Okay. And as you keep working on this, it becomes more familiar, right? What we're doing is kind of similar from chapter to chapter, just applies to different chapters slightly differently because we have different functional groups. So let's see here. With ketones, you have the carbonyl. It's kind of like the ester, but different. The carbonyl is stuck between two carbons, like that. So versus the carbonyl being on the edge, here the carbonyl is in the middle of two carbons. So you have to have this combination here, and this is called ketone. Okay, so carbonyl between, if I can spell between, two carbons. Okay, so here I reduced the number of questions so we can go through the slides a little faster. Draw out each compound clearly to show what groups are bonded to the carbonyl carbon. Okay, so we know for sure once we go to the question, we're dealing with a carbonyl carbon situation, right? Label each compound as either ketone or aldehyde. Okay, for the first one here, let's see, I got a carbon, and a carbon. So these most likely will be my middle carbons, right? My central carbons. So I'll put a C here, a C, and a C. Okay, on the left, I have three hydrogens. 1, 2, 3. A hydrogen, a hydrogen, a hydrogen. I know my carbons are surrounded by 4 bonds, so I'm going to draw 4 bonds. So I'm essentially done with this and this. Okay, next one, carbon. Okay, let me draw 4 bonds around it, 4 bonds. And it's attached to 2 hydrogens, one top, one bottom. Done. Next one, carbon. So I'm going to draw 4 bonds for right now. I may not need the 4 bonds arranged that way, so I will adapt, right? And on one hand, I have a hydrogen. I'm going to draw it on, just to be consistent with the visual, I'm going to draw it on the right. And on the other hand, I have an oxygen. What happens to this bond right here? Since we know ahead of time we need a carbonyl carbon, the carbonyl carbon has this organization right here. Then I'm going to remove the second bond and double bond it with the oxygen. Okay, so this is kind of like not really following Lewis rules, not really, but that's the quicker way to draw the aldehyde. So I know it's an aldehyde because my carbonyl is the carbon in my carbonyl is my first carbon. It's all the way to the edge and it's attached to a hydrogen, right? So I know this is an aldehyde. Judging its identity by the elements. Okay. What? Okay, these I know they're edge carbons, right? To be a middle one, most likely. Because the oxygen is here, it's most likely somewhere in the middle too. Okay, so I have C, C, O. Oops, I lingered too long. O. Okay, so this will be my first carbon, I guess, my second, my third, my fourth. My first carbon then is attached to these 3 groups. So I'll write CH3, 1, 2, 3. Okay, so I'm done with that. And then I guess I'm done with this. Let me add a bond here to be really done. This next one here, I just see a carbon. Oh, I just realized something. Because I'm like, where are the hydrogens? Okay, let me tell you something. Okay, this is what you don't do, what I just did. Okay. I didn't work this out ahead of time, so you're just flowing with me. Okay, here's what happened. I'm looking at this saying this is missing hydrogens, right? I'm supposed to put bonds here and bring in there is no hydrogens. I did the first one, the second one. So because of that, even though I thought this carbon was going to be in the middle, it can't really be in the middle. Plus, I wasn't paying attention. It says carbonyl. So technically, this oxygen cannot be in the middle. It has to be up here. Okay. Why? How did I figure that out? There is no hydrogens here to support the structure I was going with, so it won't work. So for that reason, this oxygen has to be on top. So let me change that. This is a carbon here. The oxygen belongs on the top, not on the middle, like part of the alcohol group, because I don't have hydrogens to support that structure. And then here I have a carbon. Okay. So this would then have a double bond and a lone pair, which is consistent with what it said here. You have to have a carbonyl. Okay. Then the carbon on the right, so this was the middle, it was a side group. The carbon on the right will have to have 3 hydrogens. So sometimes if you're not following the Lewis rules, you have to kind of, rearrange your atoms until it fits, like what I just did. So let me see. Let me check to verify. I do have 1, 2, 3 central atoms, right? These 3 were essentially that, and that. That was. I couldn't hear what you said. What is this phone? This watch? Okay, sorry. That's my watch. You were not supposed to be listening. Okay, so carbonyl, and you have this right here. Yeah. Oh, this is a ketone, right? Because you have the carbonyl in the middle right here, and to either side you have a carbon. So that makes this a ketone. Okay. Oh, isomers. Fun. Draw the structure of the 3 constitutional isomers. They're telling you up front. It's going to be constitutional. You're going to have 3. Draw the structure of the 3 constitutional isomers of molecular formula C4H8 that contain a carbonyl group. Okay, so they have to contain a carbonyl group. That's a requirement. Label each compound as a ketone or aldehyde. Okay, we can do this. I'm saying we can do this, and I'm like, yeah. Okay, so we need to have 4 carbons. Let me start with the 4 carbons. 1, 2, 3, 4. I'll try it out as an aldehyde and see if that works. Okay, 1, 2, 3, 4. Okay, and then let's see. I'll put my carbonyl at the end. Put my double bond here. Put my hydrogen here. Put these bonds to connect all the middle atoms, right? Put a bond up, bond down, bond up, bond down. I'm trying to make sure each carbon is surrounded by 4 bonds, right? The carbonyl, you have to have carbon double bond and then oxygen right there. So we're good. Okay, let me see if this will work. It says I have 8 hydrogens, right? Here is 1, 2, 3, 4, 5, 6, 7, 8. Oh, it works. Okay, that's one structure. How many more do I need? It says 2 more. And in each case, I have to have a carbonyl. Okay, I can't just do this on the other end because essentially the same molecule just flipped over, right? So that won't work. Let me try to make this slightly smaller. So the only other option we have right now is to put the carbonyl in the middle, right? Can we do that? Let's go ahead and try that. 1, 2, 3, 4. I put the carbonyl here and see if that will work. Single bond, and then right here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so hydrogen, 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 hydrogen. 1, 2, 3, 4, 5, 6, 7, 8. Oh, great. Second one worked. Okay, last one. Okay, so I'm thinking. Oh, okay, because I'm like, I don't think we have any other combinations with the ketone. With the ketone, you can only have this here. If you move this over here, it's the same compound. But you know what I thought about? How about we branch the aldehyde, right? So we move this carbon, we break this part off, and then we move this over here. Huh. Okay, let's try that. Let me undo this mess here. So I'm going to try with the aldehyde again. This time I'm going to have my longest chain having 3 carbons. 1, 2, 3, right? Double bond, O, H, like this. 1, 2, 3, 4, like that. Okay, now I'm bringing the the far end carbon, the one that was on the right, I'm putting this down here as the side group. Okay. Then I have 1 hydrogen plus 3 here makes 4, 5, 6, 7, 8. Ta-da! And I have 3. Okay. And so this will be a ketone because the carbonyl is between 2 other carbons. This one here is on the edge, so that would be an aldehyde. This one here on the edge also, that makes it an aldehyde. Aldehyde. Right. I was thinking cyclical, but I was like, nah, we can't do that one because we have to lose 2 hydrogens. And that would get very complicated, right? So, okay, so we're moving on and looking at the structure and properties of alcohols. So alcohols contain the hydroxyl group. Of course, you're looking at the combination COH. And then now we're looking at different kinds of alcohols. So you have primary alcohols. Alcohols are classified by the number of carbon atoms bonded to the carbon with the hydroxy group. Okay, so this is kind of how I paraphrase it. This is the hydroxy group, which represents alcohol, and this is the carbon holding it or hosting it. So how many other carbons are connected to the alcoholic carbon? Now, this carbon is not alcoholic, like it has an alcohol problem, but I call it alcoholic because it's the one that's holding the alcohol group, right? So they want to know here how many other carbons are attached to your alcoholic carbon. So the proper term for the alcoholic carbon is the alpha carbon, the first carbon attached to the functional group, right? We haven't even started using those terms yet, but for right now, how many carbons are directly attached to alcoholic. I'm going to put this in quotes because that's not a real term. Carbon. Okay. So what I do here to find this out, which is what they did, I'm like, this is the group we're trying to figure out. How many other carbons are attached to that alcoholic carbon? In this structure here, there's only one other carbon, right? Because this is a hydrogen-hydrogen. So this gets called a primary carbon. And we use either the name primary or the symbol 1 degree, which stands for primary. So this kind of alcohol is primary alcohol because the alcoholic carbon is attached to one other carbon. That being the case, look at secondary. Once again, how many carbons are attached to this carbon here? There's 1 carbon here, 2nd carbon here. This is going to be secondary. Going down the chain, right? How many attached to this? 1, 3, tertiary. So primary is the 1, right? Is when you have 2 other carbons attached to your alcohol. And then tertiary is 3. So here's the question. Have a quaternary where you have 4 carbons attached to carbon. This carbon has to be bonded to 4 other groups, right? Or at least has to have 4 bonds. If one of them has to be OH for this to be classified alcoholic, then there's only room for 3 other carbons. So the answer to my question is no. If you take this alcohol off and put a carbon there, this carbon is not alcoholic anymore because it's not attached to an alcohol. So the highest level we can have is tertiary, okay? So understanding that we're diving straight into the deep end tells you classify each alcohol as either primary, secondary, or tertiary. So here's the thing. You want to find out how many attached to your carbon that's alcoholic, right? Here, I'm going to leave the hydrogens out so we can. I'm going to draw the thing. So that's this one here. Next to that carbon, next to the OH. So this is my alcoholic situation here, my alcoholic carbon. How many other carbons are attached? As you can see, just 1. So this is going to be primary. Okay. With this one here, there's no need to redraw because my alcoholic carbon is right here, part of the ring structure. So we're trying to figure out how many carbons are attached to that carbon. Well, look to the side. There's a carbon here. Look to the other side. There's a carbon here. 2, right? So secondary. And then we're continuing here. Classify each alcohol as primary, secondary, or tertiary. Okay. Once again, I feel like the hydrogens are somewhat in the way, so I'm just going to draw it without the hydrogens. So for this one here, the carbon in the middle, right, attached to the OH on top. On the right side is a carbon. On the left side is a carbon. I mean, we have the hydrogens to fill in to make sure each carbon has 4 bonds. But my interest is this alcoholic carbon. It's attached to 2 other carbons. You probably can just see it right here, and all this extra stuff may just be extra for you, but my goal is to make sure that you're understanding, right? So I have secondary here. Ooh, this one here. There's an OH. This is our alcoholic carbon, right? So we have a 1 carbon directly attached to it, 1 carbon here. We don't care about this carbon because that carbon is not directly attached to our alcoholic carbon. Our alcoholic carbon is right here. So this is also secondary. Okay, so I'm the kind of person who is very visually distracted. I'm distracted, period. So I need to do these little things here because it helps me to focus on what I'm looking at and not look all around. Okay, down here we see, ooh, we have 2 different alcohols. So if our focus is on this alcohol situation back here, this is our alcoholic carbon. Okay, surrounding carbons directly attached to it. This carbon here, that carbon there, and that carbon there. So that carbon is tertiary. It has 3, right? On the other hand, there's another alcohol here, and this alcohol is attached to that carbon. So the question is, how many carbons are directly attached to this carbon? Well, its neighbor is just that carbon. So this one here is primary. So in this little structure here, we have both primary and tertiary, right? Because we're looking at what's attached to this, that would be that. What's attached to this, that would be those 3. Okay, so primary and tertiary. Okay, so we're moving on. We talked about all of these before. So remember, I told you guys before, when they're asking you for shape, they mean molecular geometry. So when we're looking at an alcohol, the general formula Rho, ROH, it contains an oxygen atom with a bent shape. So when we look at, we're told that this alcohol around, so looking at the atom, this shaped around oxygen. So this is your chance to look at molecular geometry again, right? I hope this, so far, this is somewhat very repetitive, right? We have done this before. We're looking at Vesper model from the Lewis structure. We're looking at shapes like our first lab that we did. It's the same thing over and over again. So I'm going to pull up my little help document over here. Okay. We're going to figure out, how do we figure out its bent shape? I mean, it says so right here, but my goal is for you guys to know how to use these resources, right? So on the left, each lone pair counts as a group, right? So this is one electron group, this is another electron group, and then this whole thing is an electron group, and this one here is an electron group, okay? So essentially around this little oxygen here, we have a total of 4 electron groups. So when you go to this table here, go find you 4 electron groups here, this peach color. With 4 electron groups, you have 4 options to pick from. Sorry, let's say 4, I meant 3. 3 options to pick from. I'm literally looking at it, but I'm saying the number. We have 3 options to pick from. So one of these columns has the information you need. Okay. Now we have 4 electron groups. I've shown you how to figure it out. Come on. Okay. This is a group. This is a group. This is a group. This is a group. Okay. So let me erase this part so we can focus on the bonding part. This is a group, this is a group, this is a group. Okay, of all the 4 groups, now remember this part says how many are bonded groups. These are showing you which ones are bonded. I have to use my mouse to write, excuse my handwriting. And then this one here says which ones are lone pairs. Okay, so do we have 4 bonded groups around oxygen? No, these are lone pair, lone pair. So we have 2 bonded groups and 2 lone pairs. So we're looking at this scenario down here, 2 bonded groups, 2 lone pairs. Okay, Since we now selected the right row, everything we need about this, wait, where can, okay, there. Everything we need is down this row right here. So when they're asking you what is the shape, they're asking you for molecular geometry. Why is the mouse? Yeah, when they're asking you for shape, they're asking you about this column. For this class, we rarely ever go over this part here. Okay, they're usually going straight to shape. What's the shape? So we're told here by this combination, the shape should be bent. Okay, so let me scoot this down a little bit. Okay, so we said it was bent, right? So we're good. We verified that. What about intermolecular force? Remember what we covered before, right? Oh, bond angle. My bad. I forgot the bond angle. The ideal bond angle, where was that? Oh, here. 109.5. You see that? My mouse is not showing. Oh, there it is. Right. 109.5. There it is. And then if you scroll down here, 109.5. Of course, if you're looking at other resources, 109.5 is the ideal. The actual is around 104, 104.5. Okay, but either one works. Either one works. What about intermolecular force? What kind of intermolecular forces do we have here? Well, since we have a OH, remember we talked about this before, right? Since we have a OH, we're going to have a hydrogen bond. For a hydrogen bond to occur, you need existence of three bonds, either OH, O directly attached to H, N attached to H, F attached to H. Any one of these three scenarios will make it possible for the molecule to hydrogen bond. So we're reviewing what we covered before, right? Alcohols have an H atom bonded to an O atom, making them capable of intermolecular hydrogen bonding. We also said before, if a molecule has hydrogen bonding, it also dipoles and London dispersion force. So it has all three because hydrogen bonding is the highest, so it has the other two. Because of that, it has very strong intermolecular forces. Okay, what does that mean? That means it will have very high boiling point, and what else is there? Just high boiling point. Okay, so real quick, I review the three common types of forces that exist for organic molecules. Remember, van der Waals or London dispersion force. These all bonds exhibit these kind of forces. So I went through, and this is when I was younger, years ago. I listed all of these. If you're thinking about it, it's right here. Pretty much the molecular bonds we deal with, they all have London dispersion force. And then dipole force, the list is less. With dipole force, these bonds have to be polar bonds to have dipole force. With hydrogen bonding, it's even more selective, these three. And remember, if it has hydrogen bonding, it also has dipole and London dispersion force. It has dipole, it also has London dispersion force. Okay. Okay. So knowing that, now that we see the property, we're now going to compare. Okay. As a result, alcohols have a higher boiling and melting point. So this is the point I was trying to make before. If you compare them with other molecules, than hydrocarbons of comparable size and shape. So trying to compare, right? They want you to see, like a defense, why alcohol has a high boiling point and that it has a high boiling point. So they try to compare. Okay, let's compare propanol. So this is one propanol, right? And it's one because the OH is attached to the first carbon. Let's try to compare this with butane. This actually has only 3 carbons. This one here has 4 carbons, okay? And so let's try to compare. What is the melting point of one propanol? Negative 127 degrees Celsius, which is a lot higher than negative 138. We can't relate to negative a lot, but this number is a lot right, further right? If you have a number line and you have negative numbers, 0, and positive numbers on the right, negative 127 will be further right compared to negative 138. For that reason, this is larger, okay? Just to relate to negative numbers. And then what about boiling point? This boils at 97 degrees Celsius, close to water. And then this one here is negative 0.5 degrees Celsius. Very, very, very far away. Okay, so this is low, very, not just low, low boiling point, and then this one here is very high boiling point. Okay, so here we're asked which compound has a high boiling point. Give me just a moment, I'll be back, but go ahead and look at this question real quick. Okay, so in context, you can see that we're trying to compare intermolecular forces, right? So let me see. Can I move this bottom one here? Okay. Well, let me see if I can move this bottom one out of the way a little bit. Can I move that? Copy. Oh, I can only copy. Ugh. Okay. Let's see. It'd be easier if I just do the Lewis structure of this, right? So for the first one, let me copy this over, copy, and draw the Lewis structure here. Okay, let's see. With this one here, CH3, these are side edge carbons, right? So this one has to be my middle carbon. So I have a carbon here in the middle, and on one side I have a OH, and I have 3 carbons on the edge. So one is up here, one is to the left, and one is to the bottom. CH3. I just drew that one, right? I got all the pieces in there. What about this one here? This carbon is surrounded by 4 CH3s. So 1, 2, 3, 4 CH3, 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 CH3. Okay, so we're going to go through the list. We're going to ask, does it have hydrogen bond, right? Are we seeing an OH? Are we seeing an NH? Are we seeing an FH? Are we seeing any of this in this molecule here on the right? No. So no hydrogen bonding for sure. The one on the right. What about the one on the left? Are we seeing a OH? Yes, right here. So we know for sure the one on the left has a hydrogen bond. If it has hydrogen bond, guess what it also has? It has a dipole and London dispersion force. Okay. Now we decided the one on the right doesn't have hydrogen bonding, right? So now we're trying to figure out what it has. We said no to hydrogen bonding. Next is, does it have a heteroatom? Heteroatom. We're asking, do we see a sulfur? Do we see an oxygen? Do we see a nitrogen? Do we see a fluorine? Do we see a chlorine? Do we see anything besides carbon and hydrogen? The answer is no. So we can say no dipole. Dipole is also out. What are we? Carbons and hydrogen. So this one here has LDF. It doesn't have any heteroatom. You kind of need to have a heteroatom, one of these other atoms, to have dipole, and even to have hydrogen bonds. So these are missing. So what was I trying to say again? Once you go through all these lists, you're like, what's the question again? Which one had a high boiling point? Of course, the one that has more intermolecular forces has the highest, right? This is going to be the highest because you're trying to break through all these bonds. You have to use a lot of energy. Highest boiling point. Yeah, that's one of those things in chemistry. You spend so much time making your point, defending your case, and then you're done. You're like, wait, what is the case again? Okay, so let's look at this one here. This is more straightforward, right? Once again, we start with the highest, hydrogen bonding. Do we see any of those three? Are we seeing OH? Are we seeing FH? Are we seeing NH? Yeah, we see OH right here. So this is hydrogen bonding. It also has dipole. It also has LDF. What about this one here? Are we seeing OH? Not to this. No hydrogen bonding. Are we seeing any of the sulfur, chlorine, fluorine, bromine, anything, heteroatom, oxygen, nitrogen, what else? Any of the other heteroatom, none to this. So no dipole. What we have left, we have LDF only. For that reason, this first one here has the highest boiling point because it has the most intermolecular forces to break through, right? And after a while, you're like, oh, I get this already. Let's move on. Because it becomes somewhat repetitive, right? Okay, solubility. Now we're seeing solubility. The rule of solubility is, for the most part, alcohols are soluble in organic solvents. Okay, they tend to be soluble in organic solvents. So of course, organic solvents means a solvent that has like carbon, hydrogen, organic stuff. It can even have carbon tetrachloride like that. Yeah, organic. Carbon. We're looking for carbon for organic. But we're told low molecular weight alcohols, the ones that have 6 or less, usually it's like 5 or less. Okay, so 5 carbons or less are soluble in water. Okay, so we're told when you have a low molecular weight alcohol, usually 5 carbons or less, these are soluble in water. But this rule is not that simple, right? Sometimes I don't like the way the author writes the book, but they're trying not to be confusing, so they're hoping that the teacher will explain the rule. The rule isn't that simple. It's not a matter of just counting the number of carbons. You're counting the number of carbons per every OH. So for every OH, every alcohol, the cutoff is 5 carbons. So it's almost like each alcohol group supports up to 5 carbons. It's like it sponsors 5 carbons. So for every one alcohol, if you have 5 carbons, the compound will be soluble. Once you bring in the 6th carbon, it stops. The solubility drops by quite a bit. Okay. So we're told here higher molecular weight alcohols are not soluble in water. Okay. So here we have 2 structures, one that's exaggerated to make a point and one that's more familiar. The one on the left is ethanol, the one on the right is 1, 2, 3, 4, 5, 6, 7, 8, octanol. Okay, so the one on the left is water soluble. It's soluble in water. Why is it soluble in water? How many alcohol groups do we have? We have 1. We know the alcohol group can support a max of 5 carbons. This alcohol group is attached to 2 other carbons, so it's good. It's soluble in water. So this is soluble in water. Okay, on the right, we have how many alcohols? 1 alcohol. We know this can support a max of 5 carbons, but how many carbons do we have here? 1, 2, 3, 4, 5, 6, 7, 8. 3 beyond the max. So what do we say? This is water insoluble. Now this here, the other way of looking at this is, yeah, it would definitely be water insoluble. No question about that. But look at what it has many of, right? It has many. So say here has many carbons and hydrogen. I didn't even need to spell it out. C and H. This portion is soluble in organic compound. Okay, so what I'm trying to say here is within the alcohol structure, you have 2, I don't want to say competing, but 2 different behaviors in the same molecule. Remember, the OH part of the molecule is more like water, right? So let me draw out water real quick so we can see what I'm talking about. The water molecule, I'm going to draw it like this, H dash O H. So the OH part here is more like water. And then this long part here is more like oil or more organic, right? We're having all these carbons and hydrogens. So the right part will be the dominant behavior in the molecule as long as you only have 5 carbons or less. When you start having too many carbons, it starts to take over, and then the whole molecule behaves as the left part, if that makes sense. We'll go over this over and over again to where I hope that we become more familiar then. As long as you have 5 or more, more than 5 carbons, 6 or more, the molecule behaves more like oil, and so it will dissolve in organic compound and something that's oily, but not dissolve in water. Okay, so here we're told label each compound as water soluble or insoluble. Okay, so to kind of make things simple for this part, we are looking for. So I'll say we are looking for number one, polar compound, because polar compounds like sugar can dissolve in water. Number two, we're looking for hydrogen bond. So water is both polar and can hydrogen bond. So we're looking for the hydrogen bond. That would be the easiest one to tell in the compound. Or we're looking for polar bond. So polar bond is more like, yeah, this one can dissolve in water too. So let's go through looking for these two things. Any one of these two can dissolve in water. So you guys can follow along as I'm doing this, right? So the easiest one to find is the hydrogen bond, right? That's the one where I'm looking for either OH, NH, or FH. FH. Let me go looking for that. Let me see. Oh, I see an OH here. Okay, I'll come back to that. I see another OH here. So once again, if I find a molecule that can hydrogen bond, so I'm going to write here, if a molecule can hydrogen bond, comma, it can dissolve in water. Okay? So you need something that can dissolve in water. Can it hydrogen bond? That's the question. If the answer is yes, then yeah, it's going to be soluble in water. So that wasn't the simple rule, right? At least that's the first requirement. Second one, if we find the OH, does it have 5 carbons or less? So here we're kind of layering the rules. It's not just one rule. Number 2, does it have 5 carbons or less? So let me examine the hydrogen bond first before we look at everything else. If a molecule can hydrogen bond, it can dissolve in water. Does it have 5 carbons or less? Okay, so these two at least can hydrogen bond. All right, here H bond, and this one here H bond. So the first part is fulfilled for these two molecules. Next thing, how many carbons does it have? There's 1 here, there's 3 here, so it has 4 carbons. Okay, great. It has an OH and it has 4 carbons, so this can hydrogen bond. So this one would definitely be soluble in water. So our reasons are getting a little deeper, right? Hold on, let me get some water. Okay, number 4. Number 4 can hydrogen bond, so it fulfills the first part. But does it have 5 carbons or less? Well, how do we find those carbons? We start labeling over here. 1, oops, I pressed the wrong thing. We start labeling. 1, 2, 3, 4, 5, 6. I'll stop counting. It doesn't qualify. It's like you haven't met the prerequisite, the requirement. Yeah, it can hydrogen bond, but it has a dominant character that overrides the OH. The OH has its own behavior, but it has this other side of it that overrides the OH. So number of carbons has crossed that threshold, so this is going to act more like an oil. So sadly, this is not water soluble. Okay, it will not dissolve in water because even though it has an OH, it just has way too many carbons. So I've written all over here. Y'all, if you have any questions, feel free to type it in the message, right? As usual, y'all know the drill. Okay, so not water soluble. Here, water soluble. Okay, this one here doesn't even have an OH. No heteroatoms. So this one here, definitely not water soluble. If you just have carbons and hydrogens, definitely not water soluble. So not water soluble. Why? I mean, it does have a double bond, but I don't see anything here that's not carbon or hydrogen. It has carbon, hydrogen only. That means it's LDF only. That means this is LDF only, so not water soluble. It has to at least be polar or have hydrogen bond to be water soluble. Okay. I guess you can write water insoluble. Either one works. Okay, let's name alcohols. Right, we've been naming a lot of compounds, right? So we're going to name again in the IUPAC system. So the good thing about naming is we're naming so much that if you hadn't figured it out before, you get an opportunity to do it over and over again. And essentially, this is kind of how the chemistry major works. People are like, well, I can't believe you majored in chemistry. I'm like, well, as once you pass the most difficult parts, I mean, there are difficult parts in every future class, but some parts begin to feel like reruns. You're like, I've been here before. Okay, we're naming again. Okay, what part of the rule is different this time? Okay, so now the part of the rule that's different is we have a different functional group, and these are identified by the suffix, the last two letters, all. You know, um, xylitol, ethanol, methanol, they end with all, right? To name the alcohol as usual, number one, find the longest continuous carbon chain that contains the carbon bonded to the OH group. So you want to find the longest chain that has that alcoholic carbon. Remember that carbon that's attached to the OH group? That has to be part of your longest chain. Number two, number the carbon chain to give the OH group the lower number. Remember, they try to number the chain so that where you have all either the side group, the double bond, that gets the lowest number. That's just what they prefer. And then apply all other rules of nomenclatures like we tie, we won't even list it. So I read things, I'm like, come on, chemist people, stop being so lazy. Anyway, they're like, yeah, you get it. The rest of it applies. Okay, whatever. Okay, we're going to give the IUPAC name of the following. We have to number our carbons. We're numbering our carbons, not the other elements, okay? So you start numbering the side of the chain that has the hydroxyl group. So here's my hydroxyl group, the alcohol group. Let me zoom in. I'll start numbering from the right. 1, 2, 3, 4, 5. So I have 1, 2, 3, 4, 5. Here's the thing. We can't assume that all alcohols have the OH on the first carbon. It could have been on the second carbon, the third carbon, the fourth carbon, the fifth carbon. So in your name, you have to specify which carbon has the alcohol, right? So let me try to follow what they're saying. Oh, they say name the longest chain like it was an alkane and then replace the ANE with all, okay? So let's do that right here. If this was your alkane having 5 carbons, you would name it pentane, right? But we know it's not an alkane because it has a functional group that's an alcohol. So replace the A and E with OL. So it becomes, oh, sorry, replace the E, not the A and E, with the OL. So this becomes pentanol. Okay, replace the E with the OL. So pentanol. But we still have to say where this alcohol group is attached. It's attached to the first carbon. So we'll write here 1-pentanol. I've seen some of you like look at different videos. I guess especially if you're way ahead of me, you're watching different videos, right? Where they write it as 1-pentanol or pentan 1-all. There is that too. So if you find that online, either one works. I'm going to stick with the one that the book is using. So, oops, pentanol. Okay, so that's the longest chain. And then the all tells you you're dealing with the alcohol, right? Okay, let's see. Where are we? Oh, side groups. Let's not forget the side groups. Now that we've numbered these, our side groups have the same name they've had before. The one with 1 carbon is called a methyl. By now you're getting used to these, right? Hopefully. Methyl. Okay. This is carbon 1, this is 2, this is 3, this is 4, this is 5. So both side groups are on carbon 3, right? So of course each of them is like 3-methyl, 3-methyl. But when you're consolidating them, these will be 3-3-dimethyl. Yeah, don't forget them dashes and stuff, because when you're typing stuff in for the exam, those rules really matter. If you leave out a dash, it's not right. Okay, so here they're bringing these two together, right? 3-3-dimethyl -1-pentanol. Between every letter and number, we have a dash. Between every number and a number, we have a comma. I know when I was learning this, I was pacing back and forth. Oh no. Oh, okay. I was say, what happened? Yeah, 3 comma 3 dash. For a second, I thought all of us were booted out, but okay, it's just Andrea left. Okay, so what happens when an alcohol is bonded to a ring? When an alcohol is bonded to a ring, then the carbon that the alcohol is attached to, the alcoholic carbon, we're told here automatically becomes carbon 1 because their goal is to make sure that that alcohol group has the lowest number, right, when you're describing it. So 1 usually gets omitted from the name, and so we go from here. Now it says the ring is then numbered to give the next substituent the lower number. So let's look at this here. Okay. So this right here is 1. This carbon here is 1. And these rules are a little tricky. So usually I usually make sure I have the rules written down somewhere. But this part is 1, carbon 1. And then you want to number this counterclockwise to give this a small number. Don't number it clockwise, right? Counterclockwise. So 1, 2, 3. So this is essentially cyclo because it's cyclic, hexanol, right? So cyclohexanol takes care of all of this. This words here describes that. Then on carbon 3, you have the methyl group. So 3-methyl cyclohexanol, right? Okay. Since we have that, let's go ahead and see if we can name these compounds here. Ooh. Okay. We have to make this real long. 1, 2. These are okay. 1, 2. We have a OH here. And then we have 4 carbons. 1, 2, 3, 4. And then we have the fifth one, CH3. So CH2, 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 because those are metal carbons. Then we have a H here. And then we have, I'll put the H3 on the end. It's the same thing. Okay, so we have to name this. In naming this, I'm going to number my carbons 1, 2, 3, 4, 5, 6, 7. Okay, so let's see. 7 is heptanol, and my alcohol is in the second carbon, so 2-heptanol, right? Yeah. Okay, what about this one here? This next one, let me see if I can make this a slightly smaller, because I need the space. I don't want to add a page. This next one here I have, I'll start with this one here because these are side groups. So 1, 2, 3, 4. So I have a OH right here. Then here I have, let's see, H, 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 H. I guess I'm going to put in all the H's. I got that one done. I got that one done. I got these two done. I'm going to add an H here. Now here I have one H. On top, I have a CH2, CH3. On the left, I have a CH2, CH3, right? So when it comes to numbering, I have to number in such a way that the OH ends up with a smaller number. So if I try from the left, 1, 2, 3, 4, OH will be number 4. If I try from the right, 1, 2, 3, that's a better numbering system to give the OH a small number. So 1, 2, 3, this is what works, right? Okay, so my longest chain is then 1, 2, 3, 4, 5, 6. I think this is the longest. So 6 will be hexanol. But on carbon 3, I have my alcohol, so 3-hexanol. And then on carbon 4, I have my ethyl group. So 4-ethyl-3-hexanol. Okay, I'm going over this part a little faster because we've been doing this for a while, right? The part that's new is just the all part, bringing in the all. Okay, so these should be the names. Let me see if I can make this a little smaller so I don't have to open a whole new page. Oh, I didn't make that thing big enough. Being lazy. Okay, let me make this a little bigger. Okay, let me see if I can put my H right here, and I can erase this one here. Okay, next one. With this one here, oh, this is carbon 1, right? Oops, it's not writing. Carbon 1, this is 2. So we want to name this part here first. So this would be cyclo because it's cyclic. Hexa because it's 6 carbons. And then all, hexanol. And we're told back here, this is one of those places where you have to come back to the rules. If the alcohol is on carbon 1, you don't have to include the 1. So come over here and I write, where is that? So this would be 2-methyl, right? On the second carbon. So 2-methyl cyclohexanol. That would be the name of this structure right here on the left. Okay. Now for this one here, let me see. I'm going to do the last two. 5-methyl 4-propyl 3-heptanol. Wow. Okay. Can I do it on this page? Okay, I'm going to do the second one and then the third one. So B and C. Heptanol is 7 hepta. 1, 2, 3, 4, 5, 6, 7. And then it says it's 3-heptanol. So I'll number this 1, 2, 3, 4, 5, 6, 7. So on carbon 3, I have an alcohol. So I've done the hepta, 7 carbons, all on carbon 3. That part is done. Then on carbon 4, I have my propyl. Propyl has how many? 3 carbons. So on carbon 4, I'm going to attach here 1, 2, 3. Okay? And then let's see. On carbon 5, I have a methyl group. On carbon 5, I have a CH3 methyl. So I'm going to fill in whatever is missing here to give me a full compound. CH2, CH2, oops, CH2, H2, CH3, okay? So this is going to be CH3, this is going to be H and H on the bottom, H on the top, H on the bottom, H on the bottom and the top, H on the bottom, the side, and top, bottom, and side, okay? You get it, right? All the H's come in to fill in to make sure each of these carbons has got 4 bonds, right? And that's the structure for B. What about C? Starting from the right, I know it has an alcohol, hexane, cyclo. So I need to have a ring structure here. Let me make this a little smaller on the right. A ring structure. So I'm going to have a ring, 6-carbon ring, right? And then one of these will have the OH. That will be my first carbon, carbon 1. So I'm done with this part here. Then I have a 3-methyl. So I'll number it, let's see, I'll number it clockwise. 2, 3, 4, 5, 6. So on carbon 3, right here, I have a methyl. So I'll leave it like that. This is a methyl, right? Represents the methyl. And on carbon 2, oh, back here, I have an ethyl. I can leave it as a skeletal structure. Remember, each corner counts for 1 carbon. Each end counts for a carbon. So I essentially just put in 2 carbons there, and that's my structure, right? Okay. So we're moving on. Like before, the ether is so similar to the alcohol, but in the place of the H that we would normally have here to have an alcohol, we have another carbon, right? So you find the ether when it's condensed, it's ROR, but it's usually really more of a COC because it has 2 alkyl groups of either side of the oxygen. Just like before, the shape will be bent because you still have 4 electron groups, right? 2 of which are lone pairs and 2 are bonds. Same thing like we saw with the alcohol, same thing with the water. So this is going to be bent, bond angle 109.5, just like before. So I won't even pull this up, right? Now we're going straight into naming this. How do we name ethers? For this class, we're going to be naming simple ethers, and we're going to be using the common name more than the IUPAC name. We're going to be using, this is a common name, okay? So it says here, using the common name system, we will name both alkyl groups bonded to the oxygen atom. We'll arrange these alphabetically, and then the final suffix will be the word ether. So it's like side group, and literally the word ether. And this is the template for naming the ether. A side group, ether. Okay? So if you have identical groups, you want to use the prefix, for example, di, etc. Okay? So here, you're looking at the oxygen. I know this is a very different way of naming. You want to know why it's very different? Because this is not IUPAC. It's not IUPAC, so it looks very different from the other ones. But for some reason, scientists prefer naming ethers using their common name versus using their formal official name. So we have to go with the flow, and we're going to follow scientists along. So look at the groups around the oxygen. This is called ethyl, like we know before. This is methyl. So order it alphabetically. I usually have to sing the song in my head, A, B, C, D. Anyway, ethyl comes before methyl, so ethyl, methyl, ether. That's it. Here we have two ethyls, so diethyl ether versus saying ethyl, ethyl, ether. Right? Diethyl ether. Okay, we're going to do that here. We'll name this 1, 2, 3, 4. This is going to be butyl, and this is methyl. This is a common chemical. It's called butyl methyl ether. They actually call it methyl butyl ether, but anyway, yeah, butyl methyl ether. And then here we have 3 carbons, propyl, 3 carbons, propyl, dipropyl ether. Yeah. Oh, okay. Like we've seen before, draw the structure of the 3 constitutional isomers of molecular formula C4H10O that contain an ether. How many of them? 3. Okay. So 1, 2, 3, 4 carbons. 4. Because the the oxygen has to be between 2 carbons, right? So let me start with the skeletal structure. No, it's not the skeletal, sorry. The core structure, the middle. Let me make that one 1. I'll fill it in. 1, 2, 0, 1, 2. Ooh, last one. Did they say 4? Oh, 3. Okay. 1, 2. I'll do this first one and break the piece from here and bring it here. 1, 2, 3, 4. Take the piece on the end and bring it here. Huh. Okay, I'll fill in the hydrogens. This will give me my 4 or my 3 structures, right? 1, 2, 3. Dot 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 dot. 1, 2, 3, 4, 5, 6, 7. Okay, so 7 plus 3 is 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Did it. 3. Okay. I try to visualize the arrangement without the hydrogens in the way, and then I can just fill in the rest, and then it works out. Okay, physical properties. So we're seeing here that we do have a heteroatom, right? The oxygen. We have carbons here, and then the central atom has lone pairs. So for sure we have a dipole. So here we're going to have dipole, LDF. Guess what we don't have? We don't have OH because there is no H attached here. So ether does not contain a hydrogen atom bonded to an oxygen, so ether cannot form intermolecular hydrogen bonds. It can only do dipole and LDF. Okay, then they go ahead and compare this with the past molecules we learned, right? So these facts give ethers. So now we're looking at ethers. Ethers have stronger intermolecular forces than alkanes. Remember, ether have dipole, and LDF. Alkanes, LDF only. They're the ones that have hydrogen and carbon only, but they're weaker than alcohol because alcohol has hydrogen bonding, dipole, LDF. Ether has dipole-dipole LDF. So it's one of those molecules right in the middle, right? Okay. As a result, ether of comparable size and shape tend to have higher melting points and boiling points than hydrocarbons. This is listing the three, right? Alkanes, if I can spell correctly, brain, alkenes, enes, and alkynes. So you got your single bond, your double bond, your triple bond. Ether surpasses that. It boils at a higher temperature, right? Because it has more intermolecular forces. But ether is humbled compared to alcohols. Alcohols having the hydrogen bond will surpass ether, and therefore ether will have a lower melting point and a boiling point compared to alcohols. Okay? So this is telling you once again, if you're comparing these three groups, the alkane, the ether, and the alcohol wins because it has hydrogen bonding, dipole-dipole, ion dispersion force. This one here has LDF only. This one here has dipole-dipole LDF, right? Now we're like, are we saying this over and over again? Yes, we are. Only because of how I set up the class, so we're saying it over and over again. Okay. Okay. Which compound in each pair has a higher boiling point? Really? Yes, yes, yes. Okay. So you can see here has carbon and hydrogen. That means it's LDF only. This one here has a heteroatom, so at least it has dipole-dipole. So this one here is higher. Okay. Let's look at this one here. What about this? This one's carbon, hydrogen, therefore LDF only. This one here is an oxygen, no hydrogen attached to the oxygen. So this one will be dipole-dipole and LDF. Therefore, this will be higher. Okay? Okay, now things get interesting. We're talking about boiling point, not solubility here, right? Boiling point. So this one here now has OH. Well, if it has OH, it has hydrogen bonding. It has dipole-dipole, it has LDF. On the other hand, over here, because it has a heteroatom, it has dipole-dipole, LDF. So now this one has a higher boiling point. Yeah. Okay. This. Ooh, they're both ethers. They're both between, the oxygens are both between two carbons. Okay. That means technically they both have dipole-dipole, dipole-dipole, LDF, LDF. So we have to look at what makes them different from each other, right? We can't say, well, intermolecular forces, they have the same kind, but do they have the same amount? This one here has a larger molar mass, therefore has higher boiling point, melting point, etc. It wins because it has a bigger structure. It has a higher molar mass. It is longer. It is more spread out. So whatever intermolecular force you're seeing it more in that molecule. So by virtue of that, this wins. This is higher. Okay. When the intermolecular forces match, you want to look at anything else to tell the difference. How are they different from each other? In this case, it is the molar mass. Okay. Oh, next thing, solubility. Just like we saw before, ethers are soluble mostly in organic solvents. These are the compounds that have carbon and hydrogen, those kind. But if you have low weight ethers, meaning 5 carbons or less, these tend to be soluble in water, as water can hydrogen bond with ether's oxygen atom. Just like what we learned with alcohols, right? Okay. So we have dimethyl ether and we're saying, so we have to make a rule, right? We said this before. In this case here, for every oxygen, I guess the cutoff point, max carbon is 5, right? Every oxygen can support 5 carbons in dissolving in water. That's our rule, right? So we have This oxygen here, we have 2 carbons. That means that methyl ether can dissolve in water. Higher molecular weight ethers, the ones that have 6 carbons or more, cannot dissolve in water, because at that point, that non-polar behavior begins to take over. So right here, the non-polar behavior takes over the molecule. You know how they say, oh, that person has a dark side. Yeah, the molecule has many sides, right? So this molecule, ether and alcohol, have a polar side and a non-polar side. So when you have 6 carbons or more, the non-polar sides begin to take over, and the molecule behaves more and more non-polar, less and less polar. Okay? The polar molecule is still in there, but it's being overshadowed by the presence of the non-polar. Okay. Label each ether as water soluble or water insoluble. Let's see. We got 1 oxygen. Check. 1, 2, 3. It should be water soluble, right? Water soluble. Because it's less than 5 carbons. Next, 1 oxygen. How many carbons? 1, 2, 3, 4, 5, 6. Once I get to 5, I stop counting. What's the point? Water insoluble. We have too many carbons. More than 5 carbons. Okay. What about this one here? There's our ether. 1, 2, 3, 4, 5. You ask me why am I counting, just because. Okay. Water insoluble. I mean, I started it, so why stop, right? Same thing here. More than 5 carbons. Okay, this part is sort of different. The last time we saw a chemical reaction with these organic compounds, we were looking at alkene, right? I think the last time we saw alkene being added to water in addition reaction to make alcohol. So one of these great techniques of organic chemistry, for those who take it as a major, is you can be an organic chemist, and the things you do is you make drugs. These are approved drugs, like FDA approved drugs, and you're a pharmacist, a legal one, right? And so your job is to make these different drugs and different chemicals. And so you want to know the recipes, quote unquote, the different ways, like what chemical, what functional group can you convert to the other functional group? And the goal is for you as a scientist to have all these notes in your head. So you know, oh, I can change this group to make this group because this is what the person needs, right? So now we're learning something called dehydration. Now, dehydration in the world of biology is you need some water, right? Drink some water. Hold on, let me get some water. It was a coincidence. Okay, but dehydration here means the loss of water from a starting material, because our context is chemistry, not biology. So it occurs when an alcohol is treated with a strong acid. So weirdly enough, the alcohol is put in a solution that has a strong acid, and then the acid removes a water molecule. And that context is called dehydration, because water molecule is literally removed from the chemical. In this case, when it removes the water molecule, what it does is it forms an alkene. Okay, so we're being told here it starts off with an alcohol. The alcohol has the OH right here. So we're focusing on the groups that are changing in the dehydration process. Remember, in this class, water is seen as hydrogen attached to an OH. So the hydroxide combines with the H and then goes off as water. And this is made possible because of the sulfuric acid, H2SO4. So this is essentially dehydration. But in the process, when this bond breaks and this bond breaks, and they go off together, forming this new relationship they didn't have before, now they're together, then the carbons form a bond with each other. So I was trying to explain this to a group of people that weren't really getting this before, and I was saying it's kind of like these are already in a relationship with each other, the 2 carbons, right? They have a bond. but they also have a bond with the groups that are about to leave. These groups leave together, forming a new compound, a new union, and then these carbons are left. There's a time where these carbons are left without partners. And so they essentially form a bond with each other to support each other through their loss. They reinforce the bond they already have. They kind of form an even stronger connection because of the loss they faced, right? When hydrogen went off with hydroxide, it left each carbon without a group right here. They form an extra bond with each other to support each other through the loss, and that's how we end up with the alkene group right here. You can look at it so many different ways. Dehydration is an example of an elimination, which is the opposite of addition reaction. Addition reaction, you're bringing two groups that were never there to begin with, so you're adding to the present formula. Dehydration is elimination. Groups leave. Okay, so H and OH leave as water, and then we have that. Okay, so you have to be able to dehydrate, remove the hydrogen and the OH. So here's the rules. The alcoholic carbon has to be attached to another carbon that has a hydrogen, or else this reaction will not happen. So that this OH has a partner to rendezvous with and leave with together as they form water. Then in the end, the alcoholic carbon now needs emotional support. Well, I guess support. And so it bonds extra with the carbon next to it. Okay? Same thing over here. The alcoholic carbon loses OH. When it loses its alcohol, the carbon next to it loses the H. So they form a double bond together, supporting each other due to the loss of the water molecule. And so this is the alkene, and this is the alcohol. Okay? I like to tell stories of reaction mechanisms. Is it necessary? No. Does it make it more interesting for me? Yes, it's more interesting for me, and it helps me remember. Who doesn't remember the alcoholic carbon losing its alcohol and facing loss and then supporting itself with the carbon next to it? I had a student laughing at me for my crazy stories, and then she went and took a test one time with a majors organic class. And then she's like, I can't remember the steps. I'm like, oh, really? Can I come to your office for you to tell me a story? She came to my office. I told her a story. She got an A on the exam. And then she's like, I'm not laughing at you again. I'm like, yeah, right. Yeah, because in the majors class, you have so many steps, like 10 steps, 11 steps. You have to remember everything, remember every bond breaking. There are all these details you have to remember. So I'm like, it gets difficult when you have to remember everything and recall it from your head. So it doesn't hurt to have a little story. Anyway, so draw the product formed when each alcohol is dehydrated with sulfuric acid. We have to find our alcohol that's going to support our our carbon that will support our alcoholic carbon. Okay, so this is my alcoholic carbon right here, right? So I'm going to pick the carbon on the left to be the one that's supporting it. Then the one on the right, I'll leave like that, okay? Because it's important for me to see where the double bond is being formed. So if these two go off together, then I'm left with essentially, I guess I can leave this as this. Let me make this a little smaller, and I think it will help a little bit. There. I get on one side the water molecule, and then these carbons form a double bond, and this is what I have, right? I have an H right here, an H right here, and an H right there. Okay. Ooh, this last one, let's see. So I have my ring structure here, benzene ring, 1, 2, 3. I got, oh, this is my alcoholic carbon. I need to draw this one out. So I need to draw this out so I can see my alcoholic carbon next to it. And I'm going to put this like this so we all can see. Okay. I like to put my OH next to the H so we can see how it goes off together. These two go off together, right? Leaving the remaining carbons to have to double bond, or else they won't have octet. Let me make this a little smaller. So this is supposed to be H2SO4, H2SO4. So on the right side, I have my water that came off. Here I have my benzene ring. I'm trying to draw this real small. And then the carbon, double bond, carbon, H, H, H. Ooh, I made it. Okay. So the carbons double bond with each other to be able to maintain that octet. Okay. Where is my carbon alcoholic? Here it is. I'm going to pick this bottom carbon here to help it out. Okay. So I'm going to draw this out in a way that makes a lot more sense. So this carbon is the one that's losing its OH, right? And then this carbon over here is losing its H. And these two are going off together. So when I get my product, H2SO4, I have, hold on. This is not the easiest for me to draw. These carbons are now double bonded. So I can put them here just to feel better. But yeah, essentially this is what I have. A double bond here. I don't need to put those two there, but you get what I'm saying, right? And then I have H2O there. Okay. So we're looking at other reactions that involve alcohols, right? This is called oxidation. In your lab, let's see. Yeah, your lab, I think this week, either the one for yesterday, will involve oxidation. So here's the thing. You saw how I lined up the alcohol, OH, and the H next to it? Now we're looking at a different kind of reaction where oxidation has this general symbol. They can give you a chemical, but if they want to be lazy because chemists, oh, they're so lazy. Instead of giving you the actual chemical, they just put O in bracket. That just means oxidation. That means this word right here. Okay? So telling you when you are undergoing an oxidation reaction, this is what you notice, right? That you have more carbon oxygen bonds, there's more of them, and you have less carbon hydrogen bonds. So the biggest thing I would say about this reaction is find your alcoholic carbon, that's this one here, and then you see how the OH is written out like this. Unlike before, the OH is written out so that the bonds can be seen here, and then the alcoholic carbon on one end loses this hydrogen and then this hydrogen also. So these two go off, and then a double bond is formed between the carbon and the oxygen. Over here, we're doing the same thing, but we're doing it between neighboring carbons, right? The neighboring carbons were supporting each other after quote unquote a loss. Now the alcoholic carbon and the oxygen are supporting each other after they both lose a hydrogen. So when they both lose a hydrogen, the hydrogen is gone, the hydrogen is gone. Well, you don't see it gone here, still here. Then a double bond forms between them. And look at that. That's what we call the carbonyl. Okay, so that is a mechanism. We're going to be using this in making the product. That's how this happens, going from an alcohol to a carbonyl compound. Okay, once again, same mechanism. Good thing when you're watching this later on at your own pace, pause it, rewind. I'm learning something new about financial stuff, and it doesn't work with my natural logic. I do a lot of rewinding. Okay, I stop, rewind, stop, rewind. I'm like, I'm going to say this tomorrow again. Stop, rewind until I get it. Okay, so as we're working with oxidation, as scientists lazily write it like this, we're told primary alcohols first oxidize to aldehydes, replacing one carbon with one carbon hydrogen bond with two carbonyls. Okay, aldehydes are further oxidized to carboxylic acid. So let me try to summarize this real quick before we go through the steps. So when we are oxidizing, before we see all the dialogue, they're saying oxidation can convert an alcohol. Depending on the kind of alcohol Oh, okay, hold on. Hey, Elizabeth. Okay, this part of the lab, alcohols and fuel do all the primary alcohols and tertiary alcohols in situation formula. And no, they don't. No, they don't. Right. So as we go through this part, you can ask me your specific questions because I put that lab together very quick, and it's the one that's from your book. So I didn't really put it together per se myself. So I haven't looked at it in detail. But as I go through this, you can go ahead and ask me your questions. Okay. Yeah, they do have different structural formulas, but primary alcohols can be oxidized. Secondary alcohols can be oxidized. Tertiary ones cannot. Okay. So I'll start with this one here. Primary alcohols can be oxidized twice. Okay, so primary alcohols can be oxidized twice, and they go through two levels of oxidations. The first level, they go from primary alcohol to aldehyde. Okay, and I'm going to show you how this works. And then from aldehyde to carboxylic acid. So this is kind of the overall, right? The overall. Yeah, like they're showing you over here. I'm going to walk you through it step by step. And then secondary alcohols, ooh, let me be consistent. Secondary alcohols can be oxidized once. So this is like the title, this is the title. Secondary alcohols go to ketones, and that's it. And I'll show you how the structure makes it possible for you to tell which one can undergo the next level of oxidation. Primary can go through two steps, first to aldehyde, then to carboxylic acid. Secondary to ketones. Tertiary cannot be oxidized. Can't be oxidized. Okay? So this is the bottom line. They cannot be oxidized at all. So one of the ways in lab, okay, that they design labs, they'll give you a mystery alcohol. Figure out what this alcohol is. So if you try to oxidize and it doesn't work, you can conclude it's tertiary. If you try to oxidize it twice and it works, you can conclude, oh, it's primary. If you can only oxidize it once, you say, oh, it's secondary, okay? So we're using the differences to separate them. So let's go back here and look at this picture right here. I really don't like what they did. Let me copy this to the next page, and then we'll sort it out from there. Is it copy? Copy. Okay, so let's look at another page here. You want to have the carbon and the oxygen side by side, right? So here. Okay, I'm going to illustrate this part here. In the first step of the oxidation, just notice this, right? These two hydrogens are leaving. Oh, sorry. I hate the way they wrote it. These two hydrogens are leaving. Okay? And this bottom one here is this. So when they go from ethanol to acetaldehyde, they're already gone. You can say here plus the hydrogen. The hydrogen has already left the group, right? So we have H2 leaving, right? From this intermediate product to the last product, what we have coming in is an oxygen comes in, if that makes sense. An oxygen comes in right here. And so when you go from the aldehyde to the acetic acid, that's the change we see. Okay, so I'm going to write it out so you can see it. In the first one here, this is my central carbon. This is my O-H. I have to write this out. So the carbon and the oxygen on top of it, the alcoholic carbon and the alcoholic oxygen are both about to face a loss. and they'll each lose a hydrogen. This goes away, this goes away through the oxidation process. And when they go away, the carbon then forms a second bond with the oxygen above. So we have this bond right here. Okay? These two go off together. So the bottom hydrogen comes up. And that's this one right here. And then this group is right here. Okay? So hopefully you're seeing it play by play as I'm typing it or writing it in. In the second step, so essentially in the first step, you're losing two hydrogens, right? In the second step, you're adding an oxygen. And the oxygen adds right here to make the carboxylic acid. So CH3, C double bond O, and then OH. So when they're telling you that you are losing CH bonds, what do they mean exactly? For these two hydrogens to leave, you see what bond has to be broken? A CH bond has to be broken. Technically, so is this bond right here. But we're losing a CH bond, right? And then for the oxygen to come in, essentially, I know it's a weird way of them explaining it. Essentially, a CH bond has to break first, then the oxygen comes between these two, so then an OH, a CO bond is formed. I don't think that is so important per se. If you can see the transition, that's the most important thing. Okay? So here you see you go from an alcohol to an aldehyde to a carboxylic acid. Okay? Does that make sense? Oh, wait. What video are you referring to, Elizabeth? Oh, there's a video in the lab about, okay. The video may have been about the lab kit or some. Okay. I don't, because I'm just now shooting this video, so I'll have to go and check out that video and see. Okay. Yeah. So now that we have this, let's see. So they're showing you here what will happen with the secondary. So the first one that we saw, that was the primary alcohol. So how do I know this is a primary alcohol? First of all, I could go through two stages of oxidation. That's the primary alcohol. The other thing is, remember the alcoholic carbon? It's attached to one other carbon. So that makes the primary alcohol. Let's see. Oh, I see what you're saying. The YouTube video. I see. Yeah, I put that lab together. I threw it together real quick, so I'm like, okay, I see what you're saying. The YouTube video. Okay, so when we're looking at this here, this is a secondary alcohol. How can I tell? Well, the title says so, but for real, how can I tell? Let me look at my alcoholic carbon, right? This is my alcoholic carbon here. It's attached to two other carbons, right? Okay, so the secondary. So remember, for me to figure out what's facing the loss, I have to look at my carbon first, and then I don't know. Okay, anyway, I'll draw this above this, on top of that. These two are facing a loss of their hydrogen. That's the first step, right? We first of all lose two hydrogens. So these hydrogens go off together, and then the carbon and the oxygen get a second bond as a result of their loss. This group just comes up here to occupy the empty space, and we get acetone. So when you take 2-propanol and alcohol, you get nail polish remover acetone. Okay? Okay. With tertiary alcohol, we cannot oxidize this because you see the hydrogen is the carbon is missing a hydrogen. We need this oxygen and this carbon to both lose a hydrogen, but the carbon doesn't have a hydrogen, so it cannot undergo oxidation. So I forget what the video, I think the video was asking you about oxidation when it came to primary, secondary, tertiary alcohols, and I think it also did phenol. If I remember that video correctly, there's a lot of videos I've watched recently, a lot. Some related to chemistry, some of them not. But yeah, essentially the ones that can, like for example, a tertiary alcohol cannot be oxidized. So if you add the, I guess, chromate ion here, you will see no change in color. That's the gist of it. Oh, I see what you're saying. Okay, same structure formula, so you're confused. Okay, yeah. So no change in color because there's no reaction. For the ones that do undergo oxidation, you have a change in color as far as your lab is concerned. Okay. Okay. So here we're told draw the carbonyl products formed when each alcohol is oxidized. So let me check. My alcoholic carbon is attached to two other carbons. Okay, so let me redraw this in a way that makes sense to me and my goals. I know that ultimately this carbon has to double bond with this oxygen. For it to do that, they both have to face that loss, right? So these two will go off, and when they go off, I will end up with that plus hydrogen. Nobody really cares about the hydrogen, but that. Oh, water doesn't have a classification. Water is attached to oxygen, so you can't classify it until you have an alcoholic carbon. So water is just water, as far as primary, secondary, tertiary is concerned. Is that what you're asking? Because my mind is going to so many possible places. Are you talking about the type of reaction or? Oh, yeah. For something to be primary, secondary, tertiary, it has to be an alcohol. And alcohol has to have carbon. So it has to have a carbon attached to an OH. Water is an H attached to an OH. So it's neither primary, secondary, or tertiary. Water is just water. Water is in the class of its own. Yeah. So primary, secondary, tertiary applies to organic compounds where you have to have COH. That's why when I was learning this, I used to go coach. People are looking at me like, what kind of crazy stuff are you saying? It helped me to remember con, coach, co. Yeah, that I have to see that combination, COH, to even start to classify primary, secondary, tertiary, right? Listen, they laughed at me, but I got the grades, okay? They laughed at me first, and then I was laughing at them later. I don't know if I had to be that weird, but, you know, it is what it is. Okay, so with this one here, we have 1, 2, 3, 4, and then we have our alcohol. So 1, 2, 3, 4. Well, I should draw this smaller. Okay, and then we have our alcohol. So I want to write my alcohol in such a way that the hydrogen that's leaving is parallel to this hydrogen here, right? Now, this one has two hydrogens, so it's like H here, 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 and then H here. Okay, so these two H's are going off together. I could have picked the bottom H or the top H, it doesn't matter. But when I do my oxidation here, I don't know what the oxidation agent is, so I just put O in brackets. Did they even say what it was? They didn't. They don't care. I don't care either. So 1, 2, 3, 4. 1, 2, 3, 4. Where do I write it? Okay, here. Okay. 1, 2, 3. Right there. This is double bond O, and then I have the H right here plus H2. Well, I can put this. You know what I realized? I'm running out of room. I can put this H up. That's fine to stick with this. Okay. This is the primary alcohol. Sorry, this is secondary. This is the primary, right? Because this alcoholic carbon is attached to one of the carbon. Because this is primary, it can undergo 2 levels of Oh, no, that's fine. That's fine. It's okay to ask the questions in the middle. I'll leave my two, oh, sorry. I need to do a second level of oxidation. So right here, I'm going to have to rewrite this as H3C for that part. CH2, I'm going to write this small in the more condensed form because it's going to go faster. Then C, double bond, O, and then OH. So what I want to show you guys here is I should have written this differently, which it's okay. I'm just going to rearrange this so it looks more like an aldehyde. It's carbon, double bond O, and then H. That's your aldehyde. When you do the second level of oxidation, you're essentially adding 1 oxygen between the carbon and the hydrogen, giving you the carboxylic acid. So some books show you the 2 different states. Some books go straight to the end. Some books will just shortcut this and go from there to the end, from the beginning to the end, versus passing through the middle. Okay, but remember, if it's a primary alcohol, it undergoes 2 levels of oxidations, which is gonna form an aldehyde first, and then it will form a carboxylic acid second. Sometimes it goes through it very fast, and then it goes straight to carboxylic acid. So wait, didn't we just do that? Oh, what products are formed when each alcohol is oxidized? In some cases, no reaction occurs. Okay, so here real quick, I have my alcoholic carbon attached to one of the carbons, so it's primary, right? So what I can do here, I'll leave it as condensed structure for this part here. This is 3, I got this part done. C, CH2, I got these parts done. This is the one that undergoes the changes. So let's see, I have carbon, 2 hydrogens here, oxygen, and then 1 hydrogen, right? So of course, these bonds break off to form that. And then the hydrogen goes off. This is my aldehyde. I know it looks a little different, but when I undergo my second level oxidation, this is my first level oxidation, then this big group here, hold on. I'm running out of space. Right, so CH3, CH, and then now the carbonyl group gets an OH group, which is essentially carboxylic acid. Now, I know the way I wrote it doesn't look like carboxylic acid. That's why I flipped them around, right? I flipped these around so it looks more like the carboxylic acid, especially if you're a visual person, that will be confusing to you. So I'm going to put this over once again so it looks more like a aldehyde. The carbonyl will be vertical, the H will be on the right. Okay, carboxylic aldehyde. Let's see, this one here is secondary because we have 2 other carbons attached to the central carbon. So for this one here, it will actually be 1 step only, 1 step oxidation. Same thing with this. We have 2 other carbons attached to the central one, 1 step of oxidation. So that should be a lot easier to complete. With this case here, let's see. The carbon is attached to an O and an H. This carbon has a H right here. Then the rest of it is on the left is CH3, on the right is 1, 2, 3. CH2, 2, CH, and this H go up, right? And so I'm going to erase that carefully. And then a double bond is formed here, and this goes off together. So this right here is our ketone. And then we have one more. I have to draw this out, so I'm just going to redraw it out again so we can see how this works out. Carbon here, it has a H. This O has a H. These H's go off together, and we get, with oxidation, so let me remove this from here because I just redrew it. We get this right here. Carbon double plus hydrogen. Okay. Once again, when you have you end up with a ketone, the one where the middle. When you alcohol, you with the carbonyls all on end. That carbonyl can be further oxidized to give you carbonic acid. Okay. So here, give me just, hold on. Okay, let's see. Let me check and make sure. Okay. So then we finally get to aldehydes and ketones, right? We saw how we form them. Aldehyde is formed from the primary alcohol, and then ketone comes from the secondary alcohol. And so remember, aldehydes, I remember learning this as RHO. Essentially, you have the rest of the molecule right here, and then on the end, we end up with CHO. Since we're moving on to aldehydes and ketones, do you have any question about, or your question is about primary or secondary? Do you feel like at this point that question has been answered, or do you still have a question? Because now we're kind of going over into ketones and aldehydes, so I feel like it might be slightly different. Or you still want to leave it for the end? I'm fine dealing with it then. Okay. Okay. So we're now spending time looking at this carbonyl group. We're told this carbonyl bond is polar. We've talked about it before. Oh, the structures. I see. I see. Okay. I guess when we get done here, do you have the structures drawn out? Which I know it would be hard for you to see the structures here because I cannot even show it. Okay, so let me get done with this and then we'll try to see if we can address that question. Okay. So in this, we're told here, oxygen is more electronegative based on the table, right? I'm looking at the SNOF list. Oxygen is the closest to fluorine. Fluorine is the most electronegative. So between carbon and oxygen, oxygen is more electronegative, right? Being closer to fluorine. For that reason, in this bond here, we're told it's a polar bond where the electrons are a lot closer to the oxygen than to the carbon. Anyway, now we're moving on to naming aldehydes. When you're naming aldehydes, you want a number starting with the carbon in with the functional group. Now we don't have alcoholic carbon, we have a carbon that is the aldehyde carbon. So you want to start numbering from there. And then find the longest continuous chain, right? So find the longest continuous chain containing the CHO group, the CHO. This is the carbon from the aldehyde group. Name it like you would an alkane, and then change the E and add al. So like methane will be changed from methane to methanol. Okay? Number the chain to put the carbonyl, not the carbonyl, right? The carbonyl from the aldehyde group at carbon 1, but omit 1 from the name. Okay? And then, like I said with chemists, like we're tired by now, so apply all the other nomenclature rules. You get it, right? Just apply it. We're not even typing it out, just apply it. Okay, so the example here is we have an aldehyde that has 4 carbons in the longest chain. You start numbering from the right. 1, 2, 3, 4. So this is the 4th carbon. Okay, so if it's 4 carbons and was a butane, was an alkane, you would name it butane. But now you're dealing with the aldehyde, so you name it butanol. Okay, butanol. But you just named the longest group. You haven't named. Oh, okay, I see. You haven't named the side groups. We have two side groups, both called methyl. So you know you're gonna have dimethyl, right? Name the positions they are in. So 2,3 dimethyl butanol. Okay, I'm not going into all the details because we've gone through that before. We have common names for certain aldehydes, like formaldehydes. I talked to you about the ants and formaldehydes also being used to preserve things that were once alive and now are dead. Formaldehyde. We have acetaldehyde, that's very common too. We have benzaldehyde used as a food preservative. Okay, so these are common aldehydes, and these are not the IUPAC name. This is actually the common name being used, where they use aldehyde, kind of like ethers, right? When you're naming ketones, just like with the aldehydes, you want to find the longest chain containing the carbonyl group. Okay, number one, name it like you would an alkane, and then change the E and add ONE. So well, we can't have a ketone with one carbon. The smallest ketone has 3 carbons, right? Because you need to have the carbon on either side of the carbonyl. So we're dealing with this situation here. So this one will essentially be, hold on a second, let me try to finish this up. This will essentially be named, if it was an alkane, it would be propane. Propane. But as a ketone, replace the E with 1. So it's propanone, right? Propanone. So let's go ahead and deal with this structure here. We're dealing with a ketone where the longest chain has 5 carbons. 1, 2, 3, 4, 5. Okay? You want to start numbering from the left because the carbonyl carbon is close to the left. And then the side group is on the 3rd carbon. So 1, 2, 3, 4, 5. Pentanone. Okay, unlike the, hold on a second, pentanone, unlike the aldehyde where the carbonyl has to be on the end, that's non-negotiable. With the ketone, the carbonyl has to be somewhere in the middle, anywhere in the middle, doesn't really matter. But you have to say where it is in the name. So pentanone, the carbonyl is the 2nd carbon, so you write here 2-pentanone to say that the carbonyl is the 2nd carbon. And then you have to talk about the side group. So we have 3-methyl-2-pentanone. I know, it's fun stuff. So we're going to be naming this right here, and I'll tell you, we're naming aldehydes, right? How do I know it's aldehyde? Because of the CHO group right here. So I'm going to try to expand this a little bit. Got 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. On carbon number, whoa, whatever, 5, I have 2 CH3 groups. Okay, that takes care of those. I have this H down here. I have 2 H's up and down. Then I have this one here, up and down. This one here, up and down. And then this will be oxygen, hydrogen, 2 bonds here, right there. Okay, so I know it's an aldehyde. That's my aldehyde group on the edge, on the far right. I'm going to number it 1, 2, 3, 4, 5, 6, my longest chain. So this will be 6. So hexane, hexanol, right? I don't have to write where it is because it can only be in one position, the edge. Right on the edge. The first carbon is your aldehyde carbon. Okay, but I do have a side group, a side chain, that's methyl. So it's 5-methyl hexanol, right? Okay, this next one, let's see. Oh, this next one is tricky. I need some more space. 1, so I'm going to try to highlight my path. 1, 2, 3, 4, 5, 6, 7, 8. Wow. You see that? So it's 1, 2, 3, 4, 5, 6, 7, 8. That's my longest chain. I think it's the longest chain. So what I'm going to do, I'm not going to leave this complicated. I mean, I guess I could if I wanted to. 1, 2, 3, 4, 5, 6, 7, 8. So I have a side group here that's 2-methyl. I have a side group here that's 5-methyl. I have a side group here that's 6-methyl. So I'm going to consolidate these three. There'll be 2, 5, 6 dash trimethyl. Whoa. Okay, my longest chain has got 8 carbons, so that should be octane. Remove the E, replace it with Al, octanol. Okay. Wow, 2,5,6 trimethyl octanol. Okay. So let's see. Let me work on this last one here because I think you guys are getting more and more comfortable, right? Chloro, of course, is chlorine. This one is heptanol, so that should be 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So this is one. I'll put my hydrogen here and my carbonyl right here. On 3, I should have a ethyl. 1, 2. On 4, I should have another ethyl. 1, 2. Let me kind of spread it around a little bit. 1, 2. On 5, I should have another ethyl. 1, 2. And the rest of them are CH3, CH2, CH2. Nope. Hold on. H here. I can't be lazy like that. CH2, CH3, CH2, CH3, H, CH2, CH3, H, H, H. Woo! I did that. Okay. Yeah, my fingers. So that will be your structure essentially after I fill in everything. Okay, when it comes to ketones, we're told that with naming ketones, while cyclic ketones numbering begins at the carbonyl carbon 1, carbonyl carbon, 1 is omitted from the name. So when we're numbering these, remember to omit 1 from the name. The ring is then numbered clockwise or counterclockwise to give the first substituent the smallest number. In this case here, this is carbon 1, this is 2, this is 3, this is 4. But when you're naming it, don't name this as 1. The 1 is implied. So that will be cyclohexane, cyclohexanone. That would take care of all of this. On carbon 3, we have our ethyl. On carbon 4, we have our methyl. Arrange the side groups alphabetically. So 3-ethyl, 4-methyl cyclohexanone. Let me see. Yeah, 3-ethyl dash. Remember, between a letter and a number and a letter, you have to have a dash. Number and number, you have to have a comma, right? So 3-ethyl dash 4-methyl cyclohexanone. Okay. And they're showing you some common ketones here: acetone, acetophenone, benzophenone. Okay. Well, these are mostly common to chemists. These are common to everybody. This is nail polish remover. Well, it used to be nail polish remover. They're now using something else that doesn't cause as much cancer. Right. Okay, yeah, I'm kind of trying to rush through this to make the video shorter because I know the video is long. But remember, you can pause, right? Okay. Let's see. I'll just do this one here and this. Okay. With this one here, you number this as 1 because that's what the rule says. This one here will be 2. So this is 3, 4, 5. This will usually be cyclopentane. Replace the E with the on, pentanone, cyclopentanone, and then we have a 2-methyl. Ooh, so 2-methyl cyclopentanone. That will take care of that. Make sure you count the carbons. Don't assume how many they are, because some of you are missing those small things by just making assumptions. Let's see. This one here, oh, here, this one is different, right? I'm going to go through and number it. I have to number from the left. 1, 2, 3, 4, 5, 6, 7. Okay? So 7 is heptane. Replace the E with the O-N-E. So heptanone. But what carbon is this carbonyl on? 3-heptanone. Okay? And then we have a side group on carbon 4. So 4-methyl-3 heptanone, right? So hopefully the nomenclature is going real fast here. Okay. Now we're told aldehydes and ketones will have a higher boiling point compared to the hydrocarbons, right? Because of course they have polar. These both have dipole. They don't have hydrogen bonding, so they're polar molecules. They are stronger in their intermolecular force compared to alkanes, alkenes, and alkynes. All the hydrocarbons. Okay. So see right here, if you compare pentane and alkane with the butanol, these have dipole LDF. This is only LDF. So of course you have a higher boiling point with the aldehyde. Okay, I'm going through this part faster because once again this is like a review, right? But aldehydes and ketones, since they only get to dipole, they are lower than alcohols because alcohol has that OH bond, right? And so alcohol can hydrogen bond. They do not have O directly attached to H, so they cannot have an intermolecular hydrogen bonding. For that reason, when you compare them, here's a ketone with the alcohol beats them as far as the boiling point is concerned because you have hydrogen bonding, you have dipole LDF. Here you only have dipole and LDF. Okay? So we are asked to compare. Okay, let's go ahead and compare these. Oh, I'm looking at the slides. I'm like, yay, we're getting close to the end. Because yeah, I'm getting fatigued myself. Okay, let's see. What do we have on the right? LDF only. No heteroatom, LDF only. On the left, we have a heteroatom, but it's not an OH. So this is going to be dipole, and LDF. So this has a greater boiling point. Okay? We're looking for OH. Ooh, there's a OH. So this has a greater boiling point. Why? It has hydrogen bonding, it has dipole, and it has LDF. Okay? Greater hydrogen bonding. Greater boiling point. What about these? You look at this, there's no heteroatom. It's all just carbons and hydrogen, so LDF only. This one here has a hydrogen and oxygen, but not in the right order, right? It says CHO. CHO just means carbonyl attached to a hydrogen. We know at least it has dipole, and it has LDF for sure. So this is still higher, greater boiling point. Okay. Okay, so what about solubility? So the same rule we saw before. It's usually actually more. The safer one is 5 carbons or less. So if you have a molecule that has 5 carbons or less, the one with 5 carbons and less, these are soluble in both organic solvents and water. But our focus here is mostly water, right? It's soluble in water when it has 5 carbons or less for every carbonyl carbon. But the molecules that have 6 carbons and more, they're insoluble in water. Why? The nonpolar portion takes over. And so the molecule behaves nonpolar because that becomes more dominant, right? So if you have a nail polish remover, if you happen to have acetone and you put it in water, acetone should dissolve in water, right? Because for the carbonyl that we have here, we have just 2 other carbons. So this should work because it's 5 carbons or less to dissolve in water. And they're showing you here why it dissolves in water, because the oxygen of the carbonyl compound can hydrogen bond with the hydrogen from the water. Okay? So as I'm trying to get us to the end. Now we're looking at reactions. So with the reactions, I kind of slow it down a little bit. Oxidation of aldehydes. Remember when we saw how aldehydes were formed from alcohols? So when I look at this as a student, I was like, wait a minute, I've seen this before. Yes, when we had primary alcohols. With primary alcohols, we had the R here, we had the OH here, and then we had the H here, and then we had the H here, and then we said these two were leaving off together, leaving the carbon and the oxygen by themselves. Therefore, they had to double bond. Yeah, so now we're kind of picking up the story from the middle, saying that if you're starting with an aldehyde, you can only have 1 point of oxidation to make the carboxylic acid. Okay, so starting with the aldehyde, you have 1 more point of oxidation. The oxygen will kind of come here and barrel between the carbon and the hydrogen, and that will be your oxidation, essentially going from aldehyde to carboxylic acid. Kind of like the second step in the oxidation of the primary alcohol, right? Once again, y'all, I know I'm rushing through this. Feel free to stop and rewind, stop and rewind. I mean, you can't rewind. Scrub. Whatever that thing, go back. I'm so caught up with lingo from having, videotape where you rewind, right? But, just go back until you get to the point and hear it over and over again. Watch different videos to kind of get the hang of this. Okay. So there's only one step to go from aldehyde to acid. Okay. So now they're finally using the actual oxidizing agent. So we have butanol here. We know to go from the aldehyde to the acid, from butanol to butanoic acid, the only transformation we'll see here is the oxygen will come between the carbon and the hydrogen to form that. So it's like you're just adding oxygen. So you're just adding an oxygen between the carbon and the hydrogen. That's it. The transformation from that to that. So the CH bond is converted to C-OH bond. Okay. Same thing over here. Well, oh, no. This can't happen, right? Because we need that CH bond. So we're told here again, ketones cannot be oxidized because there is no CH bond. Because the goal here is to have this bring in 1 oxygen between the C and the H. But there is no H here. So because there's no CH bond, this cannot be oxidized. So back to your lab. If they ask you questions, if you don't have a CH bond, so when it comes to oxidation, in oxidation, CH bonds must. Oh, we have a leak. We have a leak. There's a leak. Sorry, guys. Hold on. You hear a leak? From there. Yeah, can you get a bucket, please? All right. Sorry, y'all. Hashtag it's raining. We have a little leaking situation. He's handling it. Okay. In oxidation, the CH bond must be present for the molecule to be oxidized. Okay. Right. So the absence of the CH bond just means whatever you're looking at cannot be oxidized. Oh, then we end this section here with the chiral compounds. So that's the end of the oxidation part, right? We end this section talking about chiral compounds. I think it was one of the first labs where you had to look at chiral versus achiral. Chiral is a term to refer to compounds that have this unique behavior. So to tell you what chiral is and what chiral isn't, they use the left-hand, right-hand relationship. So essentially, if you hold your right hand and your left hand across from each other, your left hand and your right hand are mirror images of each other. That's assuming you have no scars, right? They're theoretically mirror images of each other. And so when you hold them next to each other, face to face, palm to palm, you can see how they're mirror images of each other. The thumb is in the same, it's in the mirror image position of the other thumb, right? But if you take your right hand and your left hand and try to superimpose it, lay one on top of the other, they're not superimposable. What do they mean by that? They mean that the thumbs do not end up on top of each other. So even though they are mirror images, they're not superimposable. So non-superimposable images, or in this case, structures, whatever, I just say structures, are chiral. Okay? If you don't get the hand thing, don't worry about it. But it's important that a molecule is non-superimposable to its mirror image for it to be chiral. Okay? So they're telling you what is not chiral. How can we tell something is not chiral? If you take two socks that happen to match each other, the left socks is the mirror image of the right socks, but you can superimpose it so that the different areas line up. You see that here. This lines up with that, that lines up, this one lines up. Okay? When it comes to molecules, and when you have mirror images lining up, they're called superimposable or achiral, as in not chiral. Okay, let's move on and apply this to a molecule. To determine whether a molecule is chiral or achiral, it's actually pretty simple. We must examine what groups are bonded to each carbon atom. So let me kind of fast forward and go to the carbon atoms. Okay, in order for a molecule to be chiral, it has to be, most of the time it's carbon because this is organic chemistry. The carbon has to have single bonds. So number one, like chiral carbon, I don't want to confuse that. Chiral carbon has 4 single bonds. Okay, so it cannot have a double bond. It has to have 4 single bonds. Number two, attached or surrounded by 4 different groups. That's it. So chiral carbon has to have 4 single bonds and be surrounded by 4 different groups. So for here, I'm going to make this carbon chiral. I'll just say fluorine, bromine, chlorine, iodine. I just made it chiral. So as a compound, when you get this compound here and its mirror image, it will not be superimposable. Okay? So, yeah, a chiral molecule has at least 1 carbon atoms bonded to 4 different groups. An achiral molecule does not contain a carbon atom bonded to 4 different groups. Some of the groups may be alike. Okay? So if you try to superimpose a molecule in its mirror image, you can to superimpose a molecule in its mirror image, you can perform any rotation, but you cannot break a bond. So this is if you have one of the model kits and you're trying to actually make the side groups line up. In a chiral compound, 2 of the side groups will not line up. Okay, and that's what makes it chiral. So let's go ahead and see how this is illustrated in the picture right here. This right here, I'll tell you right now, is not chiral, and the proper term for this is achiral. Why is this achiral? Because you see how these match? These 2 groups are exactly alike. So here, they are mirror images of each other, but when you rotate the molecule around, you see how the side groups all line up, the middle group lines up, the side groups all line up. For that reason, they are achiral. But if you go down here and you have very different groups, like we have right here, carbon with 4 single bonds, check. 4 different groups, check. A is a mirror image of B. Okay, they're saying here the mirror image is not superimposable. We'll see. We'll see. So here they try to line it up to see if it is superimposable or it's not. Well, the central atoms line up. The top ones do. The right ones do, but the left ones do not. And there is no way you can orient these to make them line up. They're not going to line up. You always get 2 that do not line up. For that reason, these are called chiral. Okay, well, how important is this? So when I was teaching this to one of my first classes, right, and I was a young creative teacher, many, many moons ago, they were like, well, we still don't get the significance of this. How is constitutional isomer How is that? Stereoisomer, or cis and trans isomer, right? I just call it cis or trans. Cis versus trans. And then now we have chiral. How are these different from each other? The cis and trans, remember the part of the name that makes this different is just the word cis and trans. And then you have that the same side orientation, the skeletal structure, it looks like a bucket. By the way, if you're drawing this in skeletal structure, it looks kind of like a bowl, like a cereal bowl with something on the bottom of it versus this. Okay? This is cis versus trans. Cis and trans are stereoisomers because you have important groups, the large groups having different orientations, right? Constitutional isomers, the atoms are connected so differently that they even maybe have different functional groups. The names are usually very different too. In the case of chiral compounds, the central atom is the same, the surrounding atoms are the same. So the part of the name that's different is a letter R and S. Okay, so without kind of jumping way ahead, we're told here the two mirror images of CHBrClF are enantiomers of each other, and they're not superimposable. So in the chiral compound relationship of the R and the S version, the term to describe their relationship is the word enantiomer. Okay, so my students are looking at me like we're not gonna remember. Like, we don't get the point, the significance of these terms, enantiomer, cis and trans, or geometric isomers, or what's it called, stereoisomers. We don't get that. Enantiomer will be like having identical twins. Let me tell you all a story, right? So this is me a few years ago. I'm a new teacher. I had the student, and him and I were very close. Him and I and his friend, because they're always arguing with me about I took off points from one of them's assignment, and they're like, "You took off more points from me than you did with his," and I was like, "Oh my goodness, y'all!" And so they were always complaining about something. Anyway, so I see him down the hallway, and I'm talking to him. Well, I see who I thought it was him. Okay, because I have astigmatism. I wasn't wearing my glasses. I thought it was him. I'm talking to him, and then he's just smiling. He's not saying anything. When he comes close to me, I still thought it was him. He says, I think you think you're talking to my brother. And I'm like, wait a minute. There's two of you? That's how I asked the question. There's two of you? He said, yes, we're twins. I'm like, your brother never told me there were two of you. Y'all look very much alike. And how am I supposed to know without being told there's two of you? You guys look exactly alike. He's like, yeah. In other words, he was saying, I don't know you. You think you're talking to my brother. So I'm like, snap. So this happened before I went to teach my organic class. And I'm like, enantiomers are molecules that look very much alike. If you're not paying attention, you would think they're the same molecule, but they're not. The difference between them is so subtle that scientists tend to confuse them as being the same molecule. Okay? So for the most part, their physical and chemical properties are exactly alike because look at them. You have the same composition of atoms in somewhat the same, well, very similar spatial arrangement in nature, right? So I would say enantiomers, it will be like identical twins. They look alike, but they have very, very subtle differences. Cis and trans are more like fraternal twins. You can tell they're related, but you can tell it's not the same person, right? And then constitutional isomers, these are siblings. They have the same parents, but there are times when you're like, are you all really related? Oh yeah, I guess I can see the nose. Right. So I'm trying to use a sibling relationship, right? Identical twins, fraternal twins, and then siblings. So they have something that keeps them kind of similar, right? Once again, going down the, trying to make sure I'm making progress here. A chiral molecule that is not superimposable on its mirror image is essentially, or a molecule that's not superimposable on its mirror image is called a chiral molecule. A carbon atom with 4 different groups has a chirality center. So the central atom here, central atom is chiral. Okay, so right here, This central atom having 4 different groups, this is not just a central atom, but it's called a chirality center. Okay? So you're looking at the groups, not just the first atom bonded to the carbon. Over here, look at this whole group, this whole group, this whole group, and this whole group. In this class, we're not learning how to label R and S. That's for the majors class. But we can tell these are 4 different groups. Therefore, this carbon is chiral and has a chirality center. Okay, these are looked at as a group, so they're not the same, they're actually different. Okay, we're not going to be naming these, we're just going to be identifying the chirality as being present or absent. So I won't even go into all of this. Remember, the carbon has to have a single bond, it cannot be multiple bonds. So looking at this in here, let me show you the chiral carbons. This carbon right here is chiral. It's surrounded by 1, 2, 3, 4 different groups. You see that? Okay, let me erase that and show you the right carbon, the one on the right with a different color. This carbon is chiral, surrounded by 4 different groups. Right? The one on the left here is also chiral, surrounded by 4 different groups. Like that. And then the one on the right, let me see if I can superimpose it. I don't know if that's going to be helpful at all. 1, 2, 3, and this whole 4, right? But the point is, you can see, right, as long as you can find 4 different groups around the central atom, that makes that atom chiral. So here we have 4 different groups like that. Okay. Okay. Oh, we're close to the end. Yay. Okay. Label the chirality center in the given molecules. The compounds contain 0 or 1 chirality center. Okay. So for this one here, I have to draw this carbon, my first, my second, my third, my fourth. 1, 2, 3, 4. I'm going to draw out my Lewis structure so we can see how I only have the carbons I say I have, right? My chiral carbons or chirality centers. Okay, so looking at this, let me make this slightly smaller because I need a space for the other molecules right here. Okay, this is different. This is different. This whole group is different. This whole group is different, making this carbon a chirality center. So it's 1 center. Please note, this cannot be chiral because these are alike. These 3 are alike. These 3 are alike. All the surrounding atoms have to be different. Okay. Oh, this one is an easy one. Let me do the third one. I'm going to skip to that one. There, this is different from that. This whole group is different from that, right? So this is a chiral center. I want to move this a little bit over. Let me see if I can. Okay, hold on. Copy. Let me paste it here so I can have more room to write this out. Okay, so the first carbon, 1, 2, 3, 4. First carbon has 2 hydrogens attached. And then I got a double bond here, and then there's a hydrogen attached, and a single bond, and then a hydrogen, and a OH, then a hydrogen attached 3 times. Okay, so do we have a chiral carbon here? Yes, this middle one here. How can I tell? This whole group is different from that group, different from this group over here, different from that. So that carbon is chiral. Okay, what eliminates these other ones from having a chiral carbon? See, the ones that I like, this matches that, so they cannot be chiral. This one here is a double bond. You can't be chiral with a double bond. You have to have single bonds. Okay. Okay. Label the chirality center in each drug. This is easy, right here. That one is a chirality center. This is a bromophenol phenyramine. Okay, it's the antihistamine. Okay, I don't teach this class enough to pronouncing these words enough. Okay, this carbon cannot be chiral. The hydrogens match. Same thing with that. The nitrogen cannot be chiral because it only has 3 groups around it. Okay, it has to have 3. It has to have 4 bonds, 4 groups. It has to be different. Okay, this one here also, this is chiral. These groups are different. This is huge and different and different. So we have one chiral center. Notice this is an antidepressant, trade name Prozac. These chiral compounds tend to have these weird side effects, right? So here we're being told focus on health, chiral pain relievers. Ibuprofen is an active anti-inflammatory agent whose enantiomer, remember its twin is called the enantiomer, is inactive and is sold as a racemic mixture. A racemic mixture is a mixture of both isomers. Here's the thing. I noticed it wasn't mentioned. Chiral compounds, chiral enantiomers, right? The twins, so to say, enantiomers have the same physical and chemical properties. Okay? The only thing about them that's different, the only difference, so I'll say here, the only difference is the way they rotate plane polarized light. All right, you're probably saying, what at this point? Yeah, they have the same melting point, they have the same boiling point, they have the same density, the same what? The way they interact with water. The only difference is the way they interact with light, and not just any light, a very specialized light in a machine. So if you make the twins, the enantiomers, it's hard to tell you made them until you pass them through the plane polarized light. One enantiomer rotates the light. The light usually has a certain wave. One rotates it one way counterclockwise. The other rotates it the other way. That's the only way you can tell them apart. For that reason, these chemists, I feel like I'm just kind of outing the chemists, are just lazy because they're selling the ibuprofen as a mixture of both enantiomers. Because they're so similar, chemists struggle to separate them. So what you're really paying for is for ibuprofen, but they throw you a little extra twin. Now the issue is they say it's inactive. It's not really inactive. Let me tell you something. It's not active in helping you with your anti-inflammatory purposes, but it's active in giving you side effects. Okay? It has its own chemical reaction, just not good ones. So I used to call this Jekyll and Hyde the evil twin. The evil twin is the one that you didn't plan to have, but there it is. It's hard for them to separate these two, so it's just cheaper for them to just sell it as a mixture. Here, all the best. You take it, you have a headache, you feel better, you worked out, your joints hurt, you feel better, but now you got all these weird side effects. Most of them come from the evil twin, the enantiomer, which is supposedly quote unquote inactive, right? Yeah. Anyway, so the end of the chapter. Whew, I made it. Okay. Any questions? You probably have a chance to go over this later on when you're more refreshed and stuff, but okay. Let me go ahead and close this out. Okay, so yeah, hold on a second. Just hold on. Let me